All right. This will be the first video out of a series of videos going over my advanced engineering analysis class. And that class was brutal. And I took it like, I think over a year ago. And I've forgotten a lot of it. But I still have my old exam questions and my old homework stuff. So I'm going to be going over a couple of those examples. But if I don't explain stuff super clearly, that's why. And the longer I wait, the worse that I'm going to remember all this stuff. So I might as well just do the video now. So this video is going to be on separation of variables. Yeah. Cool. All right. So let's say you have this differential equation. Where u is a function of x and t. Cool. Cool. Let me write out the boundary conditions also. So you've got a couple boundary conditions. You've got du dx at x equals 0 for all of t minus hu at x equals 0, all of t equals 0. This is a nasty boundary condition, but the idea is if you can do this problem, you can do like any separation variable problem. So, yeah, that's the first boundary condition. The next one, du dx at x equals L, t equals 0. And then you've also got an initial condition. So just based on looking at this, since u is since you have a second derivative of u with x, you need two boundary conditions for x. And since u only has a first derivative with respect to time, you only need one boundary condition with respect to time. And we call boundary conditions with respect to time, we call them initial conditions. If they start at t equals 0, which this one does. U at x, t equals 0 equals a function of x. Yeah. It could, like, what's a good example? I don't know, let's say we're solving like thermal diffusion or something, and we've got a wall, and we want to solve for temperature profile of the air above the wall. The wall would have some initial temperature profile. It could all be at the same temperature, so f of x literally could just be a constant, or there could be a profile, like it's super hot on the left and it's super cold on the right, and it decreases temperature as you go from left to right. And that would be f of x. So, yeah. That's why we could set it equal to a function. Okay. Cool. So, we know that u is a function of x and t. For these types of problems, we end up writing u as a function of x and times a function of t. Yeah. I'm sure there's a good reason why we do this instead of saying x like plus t of t. But off the top of my head, I can't think of it. I probably knew it at some point, but I don't know it anymore. But you write it like this. Cool, so let's plug this into here. So if we do that, we're going to have k d dx squared of xt. I'm gonna drop these functions of just to make the writing quicker. Yeah. Equals d dt of xt. And this would equal k x double prime t xt prime. Cool. Cool beans. So now we divide the left, or now we divide everything by x, and we divide everything by t, because we want to get all of one type of variables on one side and all of the other type on the other side. So okay, so that'll look like k x double prime over x equals t prime over t. Cool. Now we set this whole thing equal to lambda, or negative lambda. You could do positive lambda. Frankly, it won't matter, but negative lambda is nicer with the math. You just have to write less negative signs later on. Okay, so okay. This means we have two equations. We have k x double prime over x equals negative lambda. That means that k x double prime, actually, you know what I did, and it does make sense, and I was thinking about that. I also divided the k over down there. Does make sense, and it makes the math easier. Yeah, okay, so this will be x double prime equals negative lambda x. So then we'll just move that lambda x to the other side. 0. So this is equation 1. And equation 2 is t prime equals negative kt lambda. Move it over to the other side, t prime, wrong prime direction, plus k lambda t equals 0. This is equation number 2. Okay, is that what I have? That is what I have. Cool. All right, let's pause there for a second. Let's go over to our boundary conditions. So we now have to transform our boundary conditions based on this. So for this first one, that'll look like x prime at 0 times t at t minus h x at 0 t t equals 0. Is that right? That is right. Cool. And we're able to just cross these out, and we're left with x prime at 0 minus hx at 0 equals 0. So that's one of our transformed boundary conditions, and it's not that bad. The transformation is not that bad. The reason why we can cross the t's out here is because they don't impact this boundary condition. They could be whatever they want, and that doesn't impact the boundary condition. The only thing that affects this boundary condition is what x equals, because we're saying x has to equal 0. Okay, next one. Be x prime at L times t at t equals 0. And just like above, t doesn't matter. There's no restraint on t here. So what we're saying is that this has to equal 0. Yep. Cool. Give me a second. I wrote something and I want to see if I can quickly remember why I wrote it. Might have found it. Okay. I'll write it up here. Okay, so I was able to say that these two boundary conditions are homogeneous because A12 equals 1, A11 equals negative h. And because of this, it's homogeneous. Now, what does that mean? I should have looked at this before I started the recording, but you're gonna have to suffer. A12 is that. A11, no. Let's say, technically, I think it's the same thing. I think A12 equals A21, but let's say that's A21. Yeah. Okay, so if we map this equation, if we map this equation here, the thing in front of the x prime, the multiplier in front of the x prime, is A12. So A12 is 1 because there's technically a 1 in front of the multiplier, or in front of the x prime. Okay, the next thing, in front of the x, there's a negative h. In front of the x, there's a negative h. So A11 has to equal negative h. Is that what I have? That is what I have. Okay, so that's how you can prove it's a homogeneous boundary condition. I think as long as they're not functions of x or t, it's a homogeneous boundary condition. But don't take my word for that. But this is why I said it was homogeneous. And same thing here. We can say, well, okay. What would we say? I'm not going to look at what I said yet. But what should I say? I should say, all right, so this has an x prime with a 1 multiplier in the front. So I should say A12 is 1 and A11 equals 0. That is what I said. Okay, cool. Cool. Now, we could transform this, but the way I solve this problem later on is I don't need to transform it. But these two boundary conditions I did need to transform. Okay, so let's go back to here. So we've got our two equations. Let's start with equation 1. Okay. Now, we don't, oh, I'm missing something. All right, we don't know what lambda is. We don't know what number it is. We don't know whether it's positive, negative, or it could be 0. We don't know. So we have to try a couple different cases and see which case matches our boundary conditions. Like, see which case has a solution for our boundary conditions. So let's start with assuming lambda equals 0. So let's start with case 1, lambda equals 0. So this would mean that we have x double prime equals 0, integrate it once, x prime equals a, integrate it again, we have x equals a, x plus b. And x over here, it's still a function, it's not the variable x. It's shorthand for this. Yep. All right, so let's plug in our boundary conditions. Which one do I want to do first? Let's do this one first. X prime at 0 minus hx at 0 equals 0. So x prime is a. So a minus x at 0, h x at 0 would be b equals 0. So then we get that a equals hb. Cool. What's our next boundary condition? This one. X prime at L equals 0. What would that look like? That would be A equals 0. Because x prime is A, so x prime at 0 equals 0, so A equals 0. But then when we plug that in here, we get that B equals 0, so no solution. So case 1 did not work. Case 2, let's assume that lambda is less than 0. And I'm doing these in order because I know which one works. After doing it for a while, after doing a couple of these problems, you'll automatically know what lambda has to be. But in my exam, I still had to go through each one and prove that the others didn't work. And I'm glad I did, because looking back at my notes, it's very helpful. Okay, so case 2, assume lambda is less than 0. So this would mean that our equation is x double prime minus lambda, x equals 0. So normal differential equation, assume x equals e to the kt, e to the kx. Normally we say e to the lambda x, but we already have a lambda, so I just picked another letter. I picked k. Cool, so we plug this in, we get k squared e to the kt, or kx, minus lambda e to the kx equals 0. So those two things cancel out. We get k squared equals lambda. Then k equals plus minus root lambda. Okay, so now there are a couple standard solutions, and I've gone over these before, but I'll write them out here again. So if we get k equals plus minus root lambda, our solution is in the form of a hyperbolic cosine of, well, okay. It would be a cosine hyperbolic of root lambda times x, b root lambda times x, b hyperbolic sine times root lambda times x. Cool. If we get that k equals plus minus I root lambda, so if, we'll see this later on, but if we assume lambda is greater than 0, we'll get this solution, and this has a solution form of a cosine root lambda x plus b sine root lambda x. So it's not hyperbolic, it's just normal. And lastly, if we get k equals like two different numbers, or even the same number twice, well, if it's the same number twice, I'll write that down too, I guess. But let's first assume it's just two different numbers. Solution will be in the form of ax plus b e to the bx. And if we get k equals a comma a, so two of the same ones, we'll have a e to the ax, b x e to the ax. I think that's right. So if we get repeated solutions, we have to multiply one of them by x. I think that's right. So in this case, we have plus minus lambda, or root lambda. Plus minus, so we have the hyperbolic one. So a cosine hyperbolic. Cool. So that's our solution form. Now, for one of the derivatives, we need to take, or for one of the boundary conditions, we need to take the derivative. So let's just do that. X prime equals a root lambda times sine h root lambda x. And so normally derivative of cosine is negative sine, but for hyperbolic stuff, there's no negative. It just goes back and forth, sine and cosine. So that's why this term is still positive. Plus b root lambda cosine root lambda x. I think that's right. Yep. Okay, so now, first boundary condition, this one. X prime at 0 minus h x prime, or x at 0 equals 0. Boundary condition. x prime at 0 minus h x at 0 equals 0. And this equals x prime at 0. All right, so let's draw what hyperbolic sine and cosine look like. I think cosine is like that. And here it equals 1, and I think sine is like that. And here it equals, at x equals 0, it equals 0. And I think that's right. I think I looked it up beforehand. Yep, cool. So at 0, if we plug in 0 into here, this will be hyperbolic sine of 0, and hyperbolic sine of 0 is 0. So this whole term goes away for this part. So we're left with b root lambda cosine, hyperbolic cosine of 0 is 1. So it's just times 1, but I'm gonna get rid of that. So it's that minus h x at 0. So we're gonna have an a, and this whole term goes to 0. Is that right? That is right. Cool. So then we can say that a equals b root lambda over h. Cool. Second boundary condition. This one, x prime at L equals 0. Okay. So then, yeah, I see what I did here. I was very smart while taking this test. Okay. I'm gonna skip a step here because I don't want to rewrite this multiple times. But essentially, I'm plugging in a right there, and then I'm multiplying out a b from both terms. So I have a b times lambda over h sine hyperbolic of root lambda L, because we're plugging in L into the x, plus, what is that? Root lambda cos hyperbolic root lambda x of L. Is that right? That is right. Okay. So this has to equal 0. This term will never equal 0. And the reason for that is because, let's see why. Lambda's negative, L is positive, so inside's going to be a negative number, so we're going to be operating over here somewhere, I think. So on the left side. I said that it's always positive. I said that this term this term's always positive, so b has to equal 0 in order for this whole thing to equal 0. Does that make sense? Oh. I'm not exactly sure how this will play out, but lambda is less than 0, which means we're going to have a negative number inside the square root, which means we're going to be taking the hyperbolic sine and cosine of I times something. And maybe that is always positive or something like that. I'm not sure. But anyways, I said this whole term is always positive, so we have to say that b equals 0. And then when we plug this into here, a equals 0 also, and then there's no solution. Cool. This is a very long problem, I just realized. Okay, so last case is case 3. Dang it, this is going to annoy me now. Why did I say it's always positive? Maybe it'll come back to me. Okay, case 3. So we said it's less than 0. We said it's equal to 0. So the only case left is lambda is greater than 0. Cool. Which means our equation is x double prime plus lambda x equals 0. Okay, and before I even go into the differential equation stuff, there's a couple important things to write down that are going to be very, very helpful later on. So, all right, we're going to solve this using Strum Liouville, and kind of the definition, you can only solve equations using Strum Liouville if it matches this condition, and I'll write it out over here. All right, so if we can put this equation into this form, then we can solve it using Strum Liouville. So, and I'll explain what Strum Liouville is later on, but we have to first prove that it can fit into this form. And luckily for us, it does, because if we set p equal to 1, that's what I had, right? Yep, p equal to 1. It'll be the second derivative of u with respect to x, which is what we have right there. Man, I hate that. P equals 1. Cool. What about q and r? Q, I think we would set q equal to 0 and r equal to 1. Yeah. So we get that, and then it matches. And then because they're continuous in the domain, because they're literally a set number, we can do Strum Liouville. Oh, because of this, and because the boundary conditions are homogeneous, we can do Strum Liouville. Cool. So, step 1, do what we always do. Assume x equals e to the k x. So when we plug this in, we get k squared e to the k x plus lambda e to the k x equals 0. Cross those stuff out. We have k equals plus minus I root lambda. Yeah. Because we got k squared equals negative lambda. When we take square root of negative lambda, we can plot out the -1 as I. And now, we talked about this earlier, if we have this solution form, you write it out this way. A cosine plus B sine. Plus cool. So far, pretty straightforward. And then, since one of our boundary conditions has a derivative, we'll take the derivative. I think that's right. Yep. Okay. So now we can plug in our boundary conditions. I'm not even going to go up there. I have it written down over here. Yep. So this will give us x prime at 0. So go to 0. This will go to 1. So go to 1, that'll go to 0. Is that right? Yep. Cool. Cool beans. This looks very similar to right up there. Second boundary condition. Yeah. Then we plug A into there also. Gonna pull the B out. Cool. Okay. Is there supposed to be a minus in there? I think there is. I think that I'm supposed to have a minus. Right there. Anyways, it doesn't really matter. So, what do we do here? Can we say what we said up here, where this stuff is always positive, so B has to equal 0? Technically, no. And the reason why is because this is, well, okay. We can simplify this to sine of x plus, that's terrible, plus cosine of x. Let's just say that is what it is. So if I plot that, if I plot sine of x plus cosine of x, there are a bunch of places where it equals 0. Equals 0 right there. Equals 0 right here. Equals 0 right there. Equals 0 right there. Equals 0 right there. So on. There's infinite number of points where this equation equals 0. So, like, if we want to solve for, what would it be? We solve for the lambdas where this equation equals 0. And then we end up with lambda n equals, let's say, I don't know, what are some numbers that we could use? Like 2.5, 5.5, and so on. It's 2.5, 5.5, dot, dot, dot. So there's infinite number of lambdas where this solution is valid. And Strum-Liouville is basically this. You find an infinite number of lambdas where a solution is valid. That is what Strum-Liouville is. And again, you can only do that if if your initial differential equation matches that form, or can be written with that form. Okay, so based on all that, we can say that this solution fixes lambda. Because now we have, like I mentioned before, the lambda equals like 2.5, 5.5, etc. And like I've solved for those in MATLAB before, so it's doable. And this B constant, you'll see in a minute, but we can leave it there for now. This is a good enough stopping point for this. Okay. That is slightly more than half the work done. So what is next? So this was all for equation 1. We also had equation 2. So let's go through equation 2 now. And it's not going to be as long. Okay. 2. All right, so we don't have to go through all 3 cases because we know that case 3 worked. So we know that lambda has to be greater than 0. So yeah, we can keep it in the same form. We don't have to add a negative, and lambda isn't 0, so we're good. So normal stuff, let's assume that t is e to the wt. I chose w because lambda's taken, k is taken. You could pick whatever letter you want, but I just chose w. So plug this in, we get W E W T plus K lambda W, nope, E W T equals 0. So we can cross those out, we get W equals negative lambda K. Cool. And then get that T equals A E negative lambda K T. Yep, and there's only one solution, so there's only one solution here. Okay, so now set up here that U is X times T. T and X equaled this equation. Well, technically this one's X prime, but X would equal that equation when you plug in A, which is B root lambda over H cosine root lambda X Okay, and like I mentioned before, lambda, it's not an unknown number. We know it now because we used MATLAB and solved for all of the possible numbers that lambda could be. And it's infinite number of numbers. So technically, I have to write Bn because there's also a constant for each associated number, but that's fine. So that's X, and then what is T? T is A e to the negative whatever. Cool. Well, we have two unknown constants, but they're both multiplied, so we can group them as the same constant. So assume A times B equals D. So I just write D out front and we're chilling. So now we only have one unknown. And guess what? We have one initial condition. So we can solve for that unknown. And the way you solve for it is kind of nasty. All right, well, let's write it out. U at t equals 0 equals a function. So U at x t equals 0 equals fx, which equals d. All this stuff is going to stay the same. Except this, if you plug in t equals 0, you just get e to the 0, which is 1. Gotta write this bigger to match. Okay. Cool. And again, remember, there are infinite number of these lambdas. So, all right, technically, I do have to write dn because there are infinite number of n's, or d's also. Okay. So there is a standard form for finding solutions for Strum-Liouville problems where lambda is an infinite number, or there's an infinite number of lambdas for solutions. And that solution form, well, for that, we need to get a couple things. So first of all, we need to call this phi n of x. Cool. Second, we multiply both sides by r of x and phi of m. So what is r of x? Well, we found r of x earlier. R is 1, right there. And phi of m is, what's a good explanation for what it is? I don't have a good explanation, but it's literally the exact same thing as phi of m, or phi of n. So it's, I'm not even going to call it phi of m. I'm going to call it phi of n. So now, if we multiply both sides by that, we have f of x times phi of n, phi of x of n, phi n of x times r of x equals dn phi n x times another phi n of x times r of x. Cool. Don't ask me why, because you would think you could just freaking cancel those out, but apparently you can't do that. This is like the standard form of the solution. So anyways, you solve for d of n. So you divide this stuff over. And you integrate it. Yay. By the way, the r of x's just equal 1, like I just mentioned, so I'm going to drop them. So you integrate them. In this case, you integrate it from, well, because your unknown is x, you integrate it based on what x is. And x goes from 0 to L. Of f of x times root lambda over h cos. Let's see, can I do this? Copy, paste. No. Dang it. I'm not gonna redraw it, I'm gonna freaking copy it. Even if I have to sit here all day. Cool, but now, this is squared because there's 2 of them. So the top has the f of x, the bottom has a square. That's the solution. And yeah, once you solve for all of these, again, your final solution is this. So you solve for, well, okay, you have your infinite number of lambdas, and you have to solve for your infinite number of dn's. And I think dn in lambda, like, if you solve for like 10 of them, that's enough. I think if you solve for more than like 10 or whatever, there's diminishing returns. So I think if you solve for like 10 of them, that's enough. But there are infinite number of lambdas, there are infinite number of dn's, and yeah. But once you solve for all the dn's, once you solve for all the lambdas, this is your solution, where you plug this dn that you solved for into it, and you also plug in all the lambdas that you solve for into it. But yeah, that's it. That is separation of variables involving Strum Liouville. This video is probably an hour long, and it's freaking brutal. Dang it, I still want to understand this. I bet me a year and a half ago when I took this class understood it very well. Well, I did, because that's why I said it, but that is essentially, separation of variables. So we split our differential equation into two equations. We solve the first one. One of them is always going to be a Strum Liouville one, and you can automatically know which case it's going to be by knowing what lambda has to be to get a solution of plus minus I root lambda. And then once you know what the sign on lambda is, you solve the second one, and you use this nasty summation to solve for the constants. Cool. All right. I think that is it.